be aware that the molecular ions can often be missing. The largest mass peak may not be the parent ion. I'm not going to do that to you. At this point in time, that's not my goal. I'm going to teach you the basics of this. But in the future, if you were to go on in this area, realize that the molecular ion is sometimes missing. And that occurs when there's a real stable carbocation that can form and the parent ion just decomposes really quickly, so it's never detected. The base peak is different from the molecular ion. This is always the peak with the greatest intensity, the tallest peak. And this is usually because it's the most stable ion. Okay, well, let's go ahead and look at what happens if we were to do a mass spec on methane. We would see a molecular ion of 16. And what we actually see is it throws off a hydrogen free radical and forms a relatively large peak with a mass of 15. Why am I showing this to you? Because I'm just showing you that fragmentation patterns that occur are that the hydrogen free radicals can be thrown off. What is detected though? It is the cation that is detected. Likewise, if it were to throw off a methyl free radical and a proton, you would get a mass of 1 detected, but we don't ever detect that. Why? Because a methyl carbocation is much more stable than a free proton, and so you don't see it break apart in the bottom reaction. It's broken apart in the top reaction. What else would you see? Sometimes you'll see more free radicals coming off. So you're going to see a lot of little peaks in addition to some bigger ones that are more recognizable. Okay, so here is methane, and you can see that large peak for 16, and here's the loss of a proton, and then here's a loss of other hydrogens. There's a teeny tiny peak for a hydrogen free radical right there. Not a hydrogen free radical, hydrogen cation. It's usually not seen very much. If we look at this, what does this do to this peak at 17? Well, that peak at 17 is the isotope peak. So this would be for deuteriums, which occur at a very, very low rate, or for carbon-13, which occurs at a rate of 1.1%. And if I look at this, you can see this is 1.1% of 100, actually 1.2. And that indicates, that ratio right there is a good indication there's 1 carbon in there. So what is the molecular ion here? It's the one that's 16, because that's your mass of methane. Which is the base peak here. The base peak is actually the molecular ion, which usually doesn't occur. So what is 17? 17 is your carbon and deuterium. Most molecules are much more complicated than this, and we don't worry about where all the fragments come from. What we do is we look at the base peak and the other major peaks and the molecular ion, if it's there, of course, and try to make sense of the fragmentation that is occurring. Let's look. Before we get into that, I want to go into the high-resolution mass spec. High-resolution mass spec actually weigh the molecular ion to a very, very precise mass. And so you can actually determine the difference between a molecular weight that is 72, 1 digit. You're having significant digits only to the units, place 1 unit place. And so on an average mass spec, both pentane and this molecule that would be 4 carbons 8 hydrogens and oxygen, both of these would have the same mass. But on a high resolution mass spec, what you actually find is the small differences in carbon and oxygen masses are borne out in an exact mass. So you would see for pentane, you would see this exact number, and for this looks like it's like butanone or something, this would bear out with a different exact mass. And so the computer that is running this will give you an exact formula from calculating what are the possible permutations. This all results from exact masses of atoms. For instance, oxygen 16 has this particular mass, whereas carbon 12, remember we define the carbon 12 isotope of having a mass of 12 AMU. And then hydrogen 1 has this exact mass. And so those exact masses are what give us the differences in the high resolution mass spec. Other isotope peaks that are very important. These are the two isotopes of chlorine, 35 and 37. The abundance is that 3/4 of the chlorines are 35 and 1/4 is 37. So when chlorine is in a molecule, we will see this pattern at the molecular ion. It's a little flag that tells you chlorine's in this molecule. Notice it's M for the molecular ion, and then M+2. The M, there might be a little tiny peak in here due to carbon 13, but you would also see an even smaller peak over here of that same amount. But these two peaks in this ratio, 3 to 1, 2 AMU apart, indicates that chlorine's in there. Likewise, bromine has two isotopes, 79 and 81, and they're present in roughly equal amounts. It's 50-50 essentially. So what we see are two equal peaks that are M and M+2. So those flags, we get that information from them. So when we are looking at a mass spec, the first thing we always do is look at the molecular ion, see is it odd. If it's odd and it doesn't have these two peaks, then we know that it's got nitrogen in it. If we see these two peaks, then we know it's got chlorine and bromine. So that one's bromine and that one's chlorine. All right, so if I look at this spectrum, tell me, what does this compound contain? Well, immediately you look at this and you say, oh my gosh, I see these two molecular ion peaks that are roughly equal in abundance. So that's a bromine signature. Bromine has a mass of 79 or 81. So I take the lower one, 94, and subtract out 79, and what do I get? 15. If I go ahead and take the 96 and subtract out 81, I again get 15. So this is actually telling me that when you take the bromine off, this is the mass that's left. 15 is the mass of a carbon plus 3 hydrogens. So actually I can look at this and feel pretty confident that this molecule is methyl bromide. Here is another example, and in this example the mass spec is given to you as a list of peaks. This is really common. So this is giving you the masses of the peak, 80 AMU, 78 AMU, etc., and the abundance, 5% of the base peak, 100%, 15% of the base peak. So this is the tallest peak, and this is the height of those peaks in relation to the tallest peak. And of course, this is the molecular ion. Now, what is this compound telling you? The first thing that you ought to notice is that 80, 78, 5 to 15. This is a 1 to 3 ratio. That's indicative of chlorine. So I look at that and I say there must be chlorine in the compound. The next thing I'm going to do is I'm going to take the mass of 35 and subtract it from 78 or 80 minus 37. That gives me 43. 43 is the rest of the compound after you take the chlorine off. You can see there's a peak for that there. That's really common with the halogens, is that they have a peak for just the chlorine or the bromine just flying off as a free radical and leaving the carbocation behind. So this is the rest of the molecule right here, and it's showing out as a base peak. How many carbons does that contain? Well, if I divide 43 by 12, I get 3 point something. So the maximum number of carbons you can have is 3, which is a mass of 36. So a mass of 36 would be 3 carbons and 7 hydrogens. That's what adds up to 43. So this is something like propyl chloride or 2-chloropropane, something like that. Notice also that there is a difference between 80 and 65 and 78 and 63. You would see these are also 1 to 3. That mass is relatively frequent, that mass loss. What is the mass loss from here to here and from here to here? That's 15. That 15 is the same mass as that of CH3, methyl. So a methyl is being lost relatively easily. So we have a methyl somewhere in the compound, and we have this formula. What are the possibilities? Well, it could be 2 chloropropane, or it could be 1 chloropropane. Which one is most likely? Well, it's relatively common for this bond to be cleaved and a chlorine free radical, and then the propyl carbocation be formed. Likewise, same here, a chlorine free radical and then a propyl, a primary propyl carbocation. But we also see that there's a loss of a methyl occurring relatively frequently. If I were to cleave this bond and lose a methyl free radical, that would leave a positive charge here. Chlorines have non-bonding pairs that can stabilize a positive charge there. If I were to lose a methyl from here and have that go off, that would put a positive charge right here, and that would be destabilized by an electronegative chlorine skip 1 to it, because chlorine's going to put a del negative here and a del positive here, and then to have a positive here would be kind of destabilized. So this is an example of how we would say most likely this is the structure for that because of the loss of the methyl free radical. Likewise, if we had a propyl 1-chloropropane, you would see this part being cleaved and a ethyl free radical being lost. There was no peak, no major peak of an ethyl free radical. So this one's not likely to be the structure. Go ahead and try this. I'm giving you the formula. Go ahead and see what might be this compound that has the following information. You've got 58 and 56, and then 77. First of all, notice that they didn't mention other fragments as being significant. that means most likely they're not. That they weren't big enough to make mention of them. So what do you see? One major peak that is basically the loss of a bromine, because this indicates bromine. Well, let's see what that could be. If I take the 77 and I divide it by 12, I'm going to get 6 carbons as possible. So 77 could be C6H5. If I look at C6H5, whenever I see that, I always think a benzene ring. So if there was a bromine substituted on the benzene ring, that would make a lot of sense. Also, that you don't see the other fragments there, it makes sense that the benzene ring wouldn't fragment because it's too hard to cut something off of there and have it fly off. It's going to want to stay intact due to the aromaticity. Okay, the parent ion is unstable, and so it can rearrange and fragment, and I've kind of been mentioning this already. So we're going to go into this a little bit more. The alkyl free radicals can fly off, hydrogen free radicals can fly off, and you can have a carbocation that rearranges and lets whole molecules fly off. So the parent ion can be large, small, or missing. So keep that in mind. I'm not going to give you any problems where the parent ion is missing, unless I tell you that it's missing. Fragments, though, can only be detected if they have charge. The free radicals that go flying off, or neutral molecules that go flying off, are non-detectable. All we can detect is what's left behind of the carbocation. Remember this, because this will help you decipher the structure. Every time you look at the fragmentation of a molecule, regardless of the instrument, you're going to see reproducible fragmentation patterns, the same intensity for the same mass ions. And so the fragmentation pattern is considered a fingerprint for molecules. And this is what the GC mass specs that have a huge number of spectra stored up in them do. So when, let's say, you go to the hospital and it appears that you've overdosed on a drug, they might take your blood and extract it and inject it in a GC mass spec and tell the computer to look for various drugs to see if they can detect those in there. This is what they do when they do drug detection for jobs, is they actually look for small quantities of drugs that you might have been taking. So that fragmentation pattern is a fingerprint, and the computer can match those up. Fragmentation patterns for molecules that have not been identified can help you determine the structure by looking at the branching and the functional groups and figuring how can the molecule decompose. And that's what we're going to go into a little bit more than what we did in those previous analyses. You were probably overwhelmed by that idea, but I'm going to show you how to make it simpler. Because mass spec is a high energy process, we're going to see these unstable fragments. So they don't have to be a stable fragment. However, those things that are more stable are going to have a greater intensity. So when you look at a molecule falling apart, you know that it can cleave in a particular place. And when it cleaves, you can assign the free radical to one part and the carbocation to the other part. Look for which part would better stabilize the carbocation, because that one is the one that's going to form. Here's an example. If I have 2,2-dimethylpropane and I put it into a mass spec, it's going to make this molecular ion. What can it do? Well, one of these bonds can cleave off. When it cleaves off, it's going to separate right here. Where would you put the free radical? Well, really, the question you ought to say is, where would I find the carbocation to be more stable? Here on this carbon or here on this carbon? Because tertiary is so much greater stability than primary, I'm going to put my carbocation on this carbon and my free radical there. And then I expect to see a large peak for this mass. Why? Because tertiary is more stable than primary. What's another type of cleavage that we see? Another type of cleavage is something, and this is the most important cleavage that we have, is something called alpha cleavage. Let's go and look at this molecule. When I'm looking at a carbon with a functional group like an alcohol, the carbon adjacent to that carbon is called the alpha carbon. So when I have a functional group that has a carbon to an oxygen on it, the bond next to it is highly fragile and will break in a mass spec. When it breaks, which one is more stable? To have the positive charge here on the carbon that has no functional group on it, or the positive charge right here on this carbon where the non-bonding pairs on the oxygen can feed in here and stabilize that positive charge? Well, from my description of that, you probably figured out that this part is going to come off as a free radical, and this carbon is going to get the carbocation. So we get this free radical, which is not detectable, and we get this carbocation, which then is detectable. Here's another example of alpha cleavage, a carbon to a nitrogen. Here's the alpha carbon, cleavage right here. When it cleaves there, what do I make? A free radical here and a carbocation here, which is stabilized by the non-bonding pairs here feeding in to that carbocation. So what's detectable? Not the free radical, but this carbocation. Here's another type of alpha cleavage. Here is the carbon with the functional group, and here is the alpha carbon here or here. What you can have is cleaving here or cleaving here. When it cleaves here, you get the R prime free radical. When it cleaves here, you get the R free radical. What do we detect? We detect either of those things. It doesn't have to be R prime only. You could have the plain R here if this was two different sides. And you get this acyl cation, and it's stabilized by the non-bonding pairs up here feeding down to stabilize that positive charge. So we see that anytime there's a hetero atom on a carbon, any hetero atom except for, let's say, boron, any more electronegative, any hetero atom that has a non-bonding pair, what can happen? Alpha cleavage. And so we look for alpha cleavage to give us information about the structure of the molecule. Other cleavages that can make sense is when you have an alcohol, sometimes, not always, but sometimes you'll see dehydration, the loss of a neutral water molecule, and we detect the carbocation left behind. There's another one that makes sense is when you have a carbonyl that has 1, 2, 3 carbons away, you have a hydrogen, you can get this thing called McLafferty rearrangement, where this hydrogen is transferred to the oxygen, and this paracyclic rearrangement of the electrons gives us an alkene that's neutral and this carbocation that is stabilized by the non-bonding pairs on an oxygen. So what peaks would you expect to see for 4-methyl, 2-hexanol, and 2-butanone? Try to use your understanding of alpha cleavage primarily and other rearrangements or cleavages that would give you peaks in these molecules. 4-methyl 2-hexanol, let's go ahead and look and see what could happen. There's 2 possible alpha cleavages. One alpha cleavage would be here, and the other would be here. If I had alpha cleavage here, it would be the loss of a methyl free radical to form this carbocation. If I have alpha cleavage here, I would form this carbocation. Because this free radical can rearrange and put the free radical here, the most likely I would expect to see this be a bigger peak than this one, because the methyl free radical wouldn't be as stable as this free radical over here. But you would see both peaks. What else could you possibly see? Well, you probably would see a peak for a cleavage here and for here, because in cleaving here, you can put a positive charge right here, which is secondary and not too bad. Cleaving here, you could put a positive charge here, and that wouldn't be too bad. These probably wouldn't be as big a peak as the alpha cleavage, but you could see these. Another thing that you probably would see, that's possible that you would see, would be the loss of water. When you see a mass of a peak that would be the molecular ion -18, which is the mass of water, you usually can say, there's probably an alcohol in that molecule. For 2-butanone, what would you see? Alpha cleavage here and alpha cleavage here. Alpha cleavage here would give you this carbocation. Alpha cleavage here would give you this carbocation. Because an ethyl free radical is slightly more stable than a methyl free radical, this carbocation would probably be of greater intensity than this one, but they probably would be relatively close in frequency. You would not be able to see a McLafferty rearrangement here, because in order for a McLafferty rearrangement, there has to be one more carbon with the hydrogen stuck over this way for the rearrangement to occur. So there has to be 3 carbons past the carbonyl for a McLafferty rearrangement to occur.